So yeah, let's talk about binary search trees, and then eventually I'll give you midterm 2 info maybe. So we'll update the page together. So in a future lab, I will come back to this and show it to you again. Oops. I did not notice that until just now. Eventually, I'm going to give you a lab that asks you to take those expression trees that we were talking about before. I don't know, why does that always happen? Try again. Remember how you can turn a mathematical expression into a tree? You can say like 3 minus 2 plus 4, and that becomes this tree. You kind of see it. The outermost operation is the plus, and then you got the minus on the 3 and the 2 as like a child of that. So it kind of tells you that the deeper things in the tree need to happen first. Do that, then add the answer to 4. Remember all that? So eventually, I'm going to give you a lab. It might be this week, where I give you a tree like this, where at the data of the nodes, it's either a character describing some sort of process, some sort of operation, right? And these are the operands at the leaves. So you got numbers at the leaves, and every internal node that's not a leaf, called an internal node, tells you what operation to do on things. So you can recursively like take this tree and generate the fact that the answer is going to be what? 1 plus 4, so 5. And let me try to show that to you now. We can come back to this later maybe, but this is going to be a piece of your lab, all right? So you've got the base case is quite easy. It's just like somebody gives you, any leaf is just a number. And so if somebody gives you a number, it's like 3. Your answer is just whatever number is in that leaf. Like the operation, do nothing, and like if somebody says 3 on paper as a mathematical expression, the answer is 3, right? 3 is 3. So like you just give back the value there that's in your data. But the recursive case is kind of cool because, again, you have a smaller tree. This is how you can produce 5 from this bigger tree that corresponds to this mathematical expression. You can produce 5 by taking this smaller tree and this smaller tree and recursively asking it to evaluate itself, because the smaller trees are still mathematical expressions, right? And so that's going to give you just get to assume the left subtree recursively, you ask it to evaluate itself, will give you the answer for 3 minus 2. You get 1 back from that deal. And then this right subtree, it's going to give you back 4. You get to assume that happens. As long as you build up your final answer correct, you're good. And so it's just saying, how do you complete the process in the recursive case? You got a 1, you got a 4. Your job is to look at your node, your root's node, and see what operation it was. So it's a plus. That means I'm supposed to add the 1 and the 4, the things that I see, and then I can return 5 to whoever called me. So you're going to combine your left and right results using your operation that's stored in, we'll call it op, inside of that node. Does that make enough sense? Isn't that interesting? Any questions about that? So eventually I'll give you a lab where that's a thing, and we will talk about it. But I think that's what I wanted to say. Yeah. Ooh, that's a great question. Yeah, you're considering your root last. You need the answers for your subtrees first before you can even think about using your root for anything useful. Yeah, that's a great thought. You do need to evaluate your children first, so it is technically a post-order traversal, doing something other than printing this time. Very nice. Yeah, other questions? So when I give you the lab, we can come back to this slide, or you can come back to this slide, and it will make a lot more sense because you'll know like the types are involved. Like there's something called data, there's something called op. It's like it's one or the other. We'll get there. But I just want to talk about BSTs today. All right. So in terms of the abstract data type, like we can think about what kinds of things do we want to do to like describe a BST. So this is the map header. Is kind of where we're going today. In C++, you have a map header where you can associate keys to values. You can insert things. That is a, let's go to that page so we remember. Same as kind of like an unordered map, which we were looking at before, but a map has order. So it's a binary search tree secretly, but it's got key value pairs, and where's a good example of it? Probably in the constructor, maybe. Maybe not. There's something called in place that like inserts key value pairs inside of a map. associate a map from characters to integers, associate that thing with that thing, that thing with that thing. So a map lets you do that, and it's going to order it based on the keys. All right. So there's a binary search tree is one way to implement a map. And remember what a binary search tree deep down does. It is, if you got a node at your root and you go left, you can go left or right, right? Left or right. If you go left, everything in that subtree to your left in a binary search tree is completely smaller than what you see at your root here. So everything over here that I could possibly ever want to put here is going to be smaller than 4. And everything to the right here is going to be bigger than 4. That's the job of a binary search tree. Usually you don't have duplicates. But if you did, you could like set one of those to less than or equal to, greater than or equal to. So like I could put a 3 here, and I could put a 5 here. But I could not put like a 2 on this side or something like that. And you play that game for everybody. If I go right from 3, I cannot put like a 7 over here, because that would ruin the fact that I went left from 4. Like there's memory of where you came from. So what's something that's bigger than 3 and still smaller than 4 because I'm over here? So if I go to the right, it has to be bigger than 3 as well, right? I could put maybe 3.5. Maybe I'm holding floats or doubles. And that could be a 1 there. And then to the left of this 5 has got to be still bigger than 4 because it's on the right side of the 4. But it's got to be smaller than 5. So like, I don't know, 4.01 could go here. And then on the right, it could be like 4.2. Or sorry, excuse me, 42. Something bigger than 5. And also bigger than 4, though, because I went right from 4 and right from 5. So you've got history there, right? So that's what a binary search tree is all about. And you can also store values at every key. It's like this, the 4 could be the key, maybe hi, mom. Like you could put stuff there as well. You're just not using it when you're inserting, but you can get it out. All right, so that's kind of the first moral of the story. How you can build the map type is, in addition to all your keys that you're storing, like here's the root of your BST, it's ordered based on the keys, but for every key you could have an associated value. You don't need a hash function for this. You just need like comparison possibilities for your key type. So yeah, the key of your binary search tree is what tells you where to put stuff, right? That's what drives the insertion function or method, however you're doing it. And any kind of value can appear, right? Just like whatever type you want here. It could be templated even. As long as you can compare keys, you can place whatever you want next to that key, some type T. And so you can associate a key with a value, just like for hash tables. It's a little different, though. It's a little bit different. It's not constant time anymore, but it's pretty nice. We'll get to that. But the values do not have to be orderable. I hope you see that. Like you can make your own weird type that has no ordering at all. It makes no sense to want to order it, because it's only the keys that's going to move you around in this tree. Does that make sense? The value could be anything. You don't have to look at it until you search for it. Search for the key that's associated with it. So the key is what moves you around. The value could be any type, does not have to be ordered. It could be anything at all. All right. So as far as binary search trees are concerned, it's just the keys that you need like an operator less than on, something like that. Any questions about that idea? Do you see it? Like you could make a weird type for yourself, and even if you don't know how to compare it, it just can't be the key, but it could be the value associated with some key. Okay. So yeah, if we had a binary search tree, like deep down, we want to use that. What are the kinds of operations we would like to have associated with it? Like what's going to build us this BST ADT kind of thing? Like think map. Well, here's some things I'm going to want to do if I want to use my BST as like an underlying representation of something. Let's define what I like to be able to do to these things. There's my root again. So these are some good ideas, right? Let's again pretend we have key value pairs. We can do a search, right? We can do an insert. We can get a size, and maybe we want to do some removal, because that's a new thing that we wanted to talk about as well, right? So, okay, what is search? Starting from the root, you're just going to go and try to find something. And so if this is let's say I'm looking up the value, I don't know, 4. And so I'll start at the root. I'll go search for 4, smaller than 5, I'm here. Bigger than 2, I'm here. Oh, I find it. If this is a map, it's mapping keys to values. You search for the key, you want to give back the corresponding value at that key. Does that make sense? If I can store that at the node 2, I'll just go and give that back. All right. So go look for the key. If it has values, return that value. Otherwise, just be like, yeah, it was there. True. Something like that. I don't know. And then insertion is pretty much the same. You just search for where you want to put the thing. Like pretend there wasn't a 3, and like you want to come and add the 3. It's like, okay, I'll go, where would I put it? Left of 5, right of 2. Oh, it's smaller than 4, so it's going to go there. Oh, I saw a null originally. That's where I'll place it, right? That's where I'll place it. You pretend to search, and if you don't find it, you put it where you would have found it, where you were looking for it, where you found null. So you got to remember its parent and also set up the parent pointers, right? So that's insertion. Now it's there. You're always adding leaves. But in addition to keys, you could have a value there. Why not? And size is something you could keep track of, how many nodes are in your tree. There's a couple different ways to calculate the size. You could store it separately. You could make a little member variable, like add 1 plus it when you add a node, minus it when you remove a node. You could also just count all the nodes in your tree if you want to do a traversal. That's a possibility. So you have options for size. It's probably good to exchange a little space for some time. And then removal is the new kind of thing that I was having you think about last time, right? Removal is when I don't want a node anymore. How do I get rid of it? We saw that it kind of depends on, like, is it a leaf? Does it have just one child? Does it have 2 children? Is it the root even? So it gets a little more complicated the more children you have. So that's the thing. All right. So yeah, that is what you could want to do for making an ADT out of a BST. All right. That's what you could want to do. And you're going to notice like these operations are pretty much the same as our hash table operations, aren't they? So the question is now, like, why in the world don't we just use a hash table for everything? What's the point of a binary search tree if we're going to use it kind of like a hash table? Well, there are some things that you can do with BSTs that you cannot do with hash tables. Notice that there is ordering, right? You go left, something's smaller. You go right, something's bigger. You do not have that in hash table land, right? All hash table is, like, you got indices, mapping them to values at those indices. Like, you place things there. There's no, like, it's just wherever you, like, the index where you place something just depends on where your hash function took you. It's going to jump all around, right? It's jump completely all over the place. There's no ordering. You cannot easily find, like, all right, what was the, like, think about 5. Like, where is the next smaller key if this were a hash table? You just kind of have to visit every index, right? Because you're not sure where it would have been placed because you don't even know what it was, right? But for a binary search tree, you have some good, very strong guarantees about where the next smaller key is, right? You know for sure it's nowhere over here. If I go left, I'll probably be able to find it. It's the biggest thing that way, yeah? There's an algorithm sitting there somewhere. So, like, those are some questions you might need to ask one day, all right? So that's when order matters and you still want key value pairs, a binary search tree is the way to go, all right? So that also helps you retrieve values within a range that you can imagine. So, all right, give me the smaller thing after that, the next smaller thing after that, just until I hit the smallest element. So yeah, there's an idea of I can go and get, like, all the elements from 2 to 5 very easily. Like, smallest value I care about, biggest value I care about. I can do a traversal and skip a lot of nodes because I have some strong guarantees. Like, I don't have to go left of 2 once I find 2, for example. Like, that's important. For a hash table, it's just like, all right, the hash function could have placed those values anywhere. You have to visit every single index in your hash table. Whereas for a binary search tree, you have guarantees. You can chop off pieces of your tree. Okay, so that's how that works. So I hope that makes sense. So ordering is important. Of course, you can do a traversal of all the elements by keys in order, because we have an in-order traversal now. You can do other weird ones as well, but it's just everything is placed in a nice spot that's different to hash tables, right? You could sort the values by key, I guess, if you want to waste some space, but you'd have to visit every single index of your hash table because you're not sure where things were placed. They were placed out of order, just like wherever the hash function took you, okay? And if there were collisions, and then also you have to consider how you handle those collisions. You just have to visit every single index. It's disgusting, okay? So yeah, I hope that makes sense. That's a thing. Technically also, you save a little bit of memory is important, like you're working on an embedded device or something where you don't have a lot of memory involved. You don't have to make more space than you have nodes. For a hash table, you kind of want, like, double the amount of indices open so that you don't collide too often. But for a binary search tree, it's like you place the stuff, you have one node per key value pair. You don't need any extras laying around for later. Just like you make them when you need them. Yeah. So that's interesting in itself, I guess. So that's a thing. Yeah, you don't ever need to make a table with more rows than you might need to deal with collisions, because there's no concept of collisions in a binary search tree. There's a concept of it's unbalanced. There are ways to deal with that. I'm forcing you to read about those things. I won't ask you to write them in code in this class, but you'll at least read about them. There are ways to handle that. But yeah, I hope that is motivation enough. Like, okay, this is a contender in that key value pair space that makes sense to want to do something about. Okay, so yeah, are there any questions about this idea? Like, these are kind of the operations that a binary search tree is good at. And so if we wanted to build an ADT and call it like a map or something, like these are the ones we want to maybe start with. Yeah. All right. So yeah, just let me have any questions. Eventually, I'll give you a question, but let's talk a little bit more. So we've got. I want to do all of these for you. Maybe. Oh man, good for us. So yeah, let's do this. So first of all, here's what our trees look like. If I'm gonna make a BST class or something, I don't know. Call it map if you want to. I call it BST. Why not? First of all, what are we going to store? We're going to store a bunch of tree nodes, right? Those are going to be the things in our trees. You can have, in addition to left-right pointers, keys, you can also have a value. Maybe if you want to do like a phone book or something, or like a reverse one. So that's a thing. Yeah, as long as you can compare stuff. And yeah, you can associate keys with values, just like add another thing in the struct. That's fine, okay? But as far as your BST class goes, your ADT, it's got like, you have all the things. You have your search, insert, size, remove, put all those things as your public things. And then your private member variable, the one thing you need to represent your BST with is where is the root. That's all you really need. You can get anywhere from the root. So you're going to say tree node star root. Okay, so that's how that's going to work. Let's see. Do I want to do that? Eventually. So I do want to write some code for you, but I guess we can do that. Is now a good time is the question. Let me check my notes. I think so. Yeah, why not? Why not? So yeah, does this make sense? Like key and value. That's fine. So we can write code. We can wrap it around the stuff that we've already done more or less. We've got let's see. We've already got some code that we've written with search and insert. We can just add on to them. We want to give back a value instead of something else. So like that's totally a thing. Maybe I don't need to do that. Yeah. So I'm going to show you, I'm going to write some code later, but you can imagine that search and insert is going to be very much the same. It's just in addition to the key that you're inserting, just also add the value. That's going to be fine. Okay. So those are the things involved. Okay, I understand where I'm going to write code now. But also the complexity is the same, and we've already talked about. There's no difference. It's still a binary search tree. It's still a tree at the end of the day when you're searching for stuff. We have some guarantees about where things are going to be. The worst case, you're getting to the bottom of the tree, right? You're following all the nodes. You're getting to the lowest leaf maybe, and then you try to like go left or right from there to find something that's not even there at all. So like that's the worst possible case scenario. You get all the way down to the bottom of the tree and you don't find the thing you're looking for, right? So yeah, let's talk about that again. So your search, for example, like you start at the root. It's like, all right, I'm looking for 3.5 or something. That's kind of the worst case. Like, all right, start here, go left, because 3.5 is smaller, go right because 3.5 is bigger, go left because 3.5 is smaller, go right because it's bigger, and now you've traversed as many things as you could possibly traverse, right? You've gone down the height of the tree, and so I will say that this is O of H time, where H is the height of the tree, all right? So that is the complexity of that, and insertion is pretty much just search plus make a node and put it at the parent, at the place where we couldn't find the thing. So like if you were searching for 3.5 again, you're trying to insert 3.5 this time, you're going to get to there and you're going to notice that there's, to the right of the 3 node is nullness. Well, make the node on the heap. That's constant time. Remember where you were, where you used to be, call that n or something. Set some pointers at the parent pointer of this guy. It's all constant time after that, and so searching was the bottleneck. Yeah. Any questions about that? Do we remember that? So, yeah, if we are good, I think you can imagine how this is going to work. Just like add a value as well. Give back the value instead. But I have a question for you now. So here, let's say we have a binary search tree. Hello, it's got a root. We're representing it with our root. All right, we can go left, we can go right. Like maybe this is the tree, I don't know. You know the worst case times of searching. You know the worst case times of inserting. What about size? What is the worst? So my question to you is, among all the different ways that you could implement size, the size operation to tell you how many nodes are in your tree, what's the minimum worst case? Does that question make sense? So there might be a bunch of competing algorithms and they all have worst case complexities. What's the minimum possible worst case complexity for running time for a size operation on a BST? I want the best worst case, all right? Because there are some options, and I think I kind of said a little bit, but if you guys could talk about it and think about it, I think that would be helpful for you. So here, I'll open up the written nice page and clear it out. If you would like to place something there, I'd appreciate it. So get together as groups, say hello to everyone, talk about how nice the rain is, and then try to come up with an answer to this in like big O notation, please. Like, what's the minimum possible worst case running time for doing size? Like, you have some tree, you need to figure out how big it is. What could you do? What could you do? Can you think of a couple different ways to implement size, maybe? Say you have total control. You have total control. You can do whatever you want as far as implementation goes. And we just care about running time. But the thing is that it wouldn't work. This is out. All right, another minute or so to think about things and write it down. It's just O of something. All right, that's my timer. Take another few seconds to write down what you came up with.
Did it work?
All right. See what we're thinking. We can do. Those are kind of the two contenders. Like, is it linear or is it constant? And I think it will be constant. What could we do to make it constant?
We keep track of the size.
Yeah. That would make it, and that wouldn't ruin anybody else either, right? Just like a plus plus on insert, minus minus on removal. That would still keep the same time complex. That's a constant time addition to those things. Good.
Yeah.
It wouldn't be too bad, right? So like if I made a size variable, I'm wasting 4 bytes for constant time. Seems like a good deal, right? Size starts at 0 with your constructor maybe. Every time you insert, you add 1. Every time you remove, you can subtract 1. As long as you make sure like the things were actually there. Because remember, the insert sometimes updates. Like you don't want to do plus plus then. Like you do have to use like an if statement or something. Like that would turn it into constant time. Does that make sense to us? It would be an addition of constant space, so that doesn't really change the space complexity. But constant time would be great. Yeah? Lovely. So, the other option though, if memory is tight, like you really don't want to add a size member variable or something, you could say that we could perform a traversal, right? That's your other option. You can traverse your tree, and then instead of like printing out every time you're at a node, you could add 1 to some variable. So technically for a split second, you need some extra space anyway. But if you didn't want to add a member variable, you could keep track of the size every time by just recalculating it, going through all the nodes with a traversal, and that would be a linear time thing. Traversal. Because you got to visit every node, you find all of them, notice each of them, please, and then count them that way. Does that make sense why those are your 2 options? So I think it would be a good idea to add a size member variable. That's useful. So yeah, here's that all spelled out now. So here's what you could do. Like add an int size member variable and like make it happen. So yeah, option 1, save that, add and subtract 1 every time you insert remove. Size is constant, and because you just return this value, whatever is there, right? So return the value of a member variable, you are set, you are golden. 0, insert some stuff, add 1, add another 1, just give back whatever's there. Your option 2 is traverse the tree. You can do any kind of traversal, pre-order, post-order, in-order, do level order with your queue, right? So that would be great. Whatever you want. So, and you're going to visit every node, doing constant work at each node, which is like plus-plussing a variable, like a global variable or something. Something like that, you could get a linear time thing that way, because you got to visit every single node, notice all of them, notice that they're there. Okay, so that's size and how it would go. And I think that is as much as I could say about it. You have options. This is a trade-off that you could be making, and that's the whole point. This is CSCI 41 in action. It is up to you to decide which option is the best option for you. Like maybe if you're not going to run size too often, I don't know, and memory's tight, maybe you don't want this. I'm not sure. It depends. So yeah, that's the idea. And I think that's all that I wanted to say about it. Are we ready for the removal algorithm? That's the hard one. All right, I'm excited. So yeah, definitely pay a little bit of extra attention. This is traditionally a difficult concept. It is very weird, especially in the 2 children case, as I'm sure you have discussed with the people sitting next to you from last time. Oh man. Is a little weird. So, though sometimes it's not too bad. So you want to remove a node, you don't like a node, you want to get out of your binary search tree. Some nodes are easy, like a leaf. Like if I want to get rid of this 1 node right here, I am in luck, because I can just, all right, search for it, remember who its parent was, and just have the parent forget about it. Just like say, oh yeah, the left of 2 is now null. Yeah. Do that. Also delete it from the heap, of course, so that you don't waste memory. But that's not horrible. When you have a child or 1 child or 2 children, it gets worse, right? 1 child is not too bad, because you kind of know what needs to happen. Like somehow this needs to do that.
Yeah.
I think you can see that. Even if there are things underneath it that would preserve ordering, it's still fine. But like, how do you notice like which side of what everything's on? It's a little weird. It's like if I want to get rid of that one, like what happens? Interesting. We'll figure this out because you got to change parent pointers as well. Like that's got to do that. That's got to do that. Kind of intuitively, you can see that. But like, how do you code that? Is the question. And then it gets even worse when it's the root. It's like, what in the world? I want to get rid of this. That's even more exclamation points and question marks, right? Something like that. So, if you were to chop off the root, you'd have two separate trees. Maybe you can just like take all these nodes and insert them into this one, the bigger one. I don't know. You can play a game like that, but there's a better way. And so we need to discuss it. All right, it's complicated. It's not normal. We will get there. Okay. So to get there, we need a new operation, and I kind of hinted at it already in just a silly example earlier today. But I want to give a name to that kind of operation. I'd like to be able to get the predecessor and the successor of a node in the tree. Okay? And what I mean by that is the next smaller key value, or the next bigger key value. So the predecessor of a node is the previous in-order node in the binary search tree. The successor of a node, you give the pointer to it, is going to start there and go looking for the next node in order in the binary search tree. So here are some examples. So like if I have 2, what's the predecessor of 2? The next smaller thing in the tree, it's 1, of course. There's only one option. There's only one thing smaller than 2 in the tree, right? The successor of 5 is 7. It's the next bigger thing in the tree, yeah. And then sometimes it's a little weird. The successor of 3, what's the next bigger thing in the tree? It's 4. It's up the tree from it. That's a little weird. So the algorithm's a bit complicated. It's going to be symmetric. I teach you predecessor, you can easily do successor, or vice versa. Okay, so I'm going to do successor. So I'm going to implement successor for you. All right, and here is the trick. All right, here's going to be the algorithm. It's going to be either, just like I showed you, the successor of this 5 was 7. The successor of 3 was 4. Sometimes you go right, sometimes you go up. All right, that's going to be the case here. So let's implement successor. So usually the successor of a node is going to be like, if that node has right children, it's the smallest right child. Does that make sense to us? So like the successor of 2 is 3, because it's like, look at all the children of 2, it's the smallest child. The smallest right child, the smallest thing that's bigger than it. Does that make sense? That's what successor is. That's what it means to be the successor. If you have right children, go find the smallest one. The successor of 5, therefore, is 7. The smallest right child. Successor of 2 is 3. It's the smallest right child. Successor of, yeah. And yeah, that's how that's going to work. Nobody else has right children. So those are the 2 good options for me right now. So yeah, that's how that works. Just, you want to go and find essentially the minimum value of the right subtree. So the minimum node, you can always get the minimum by going left forever. So like the minimum node in this entire tree, you start from the root, you just keep going left as long as you can. Do you see how that's going to give you the smallest possible thing? Just due to the nature of a binary search tree. So yeah, usually the successor can be found in that way. It's like the smallest node to the right. Smallest node to the right. Beautiful. So that just means, like, to get to the 3, for example, you go right and then you go left as long as you can. As long as humanly possible. All right? Go right. Go left forever. That's going to be the algorithm. Usually that's the case. Go left forever. As long as you can, as long as you still got nodes, all right? If there is no right child, usually there's still a successor of you. It's just going to be one of your parents. It's going to be guaranteed that your successor is one of your parents in that case, which is interesting to think about. So what you do in this case, if there is no right child and you're looking for a successor, you have to go up. You follow parent pointers until you find the first bigger thing. The first bigger thing is guaranteed to be your successor, all right? So that's at least how I want to teach it to you. Your book's going to explain it in a different way. And I think it's useful to learn both ways. But say you're looking for the successor of 3, you just go up and you notice, oh, the next bigger thing was 4. Something like that. So that will 4 is bigger than 3, so I stop. Like, that's got to be my successor. And the reason that works is because 3 exists on the left side of, 3 exists on the left side of 4, which means that the 4 was bigger than it, and it was the next bigger thing, okay? Just because of that. Like, go up until you come at your parent from a left child, essentially. That's another way to explain it. But I like thinking about it as like, just remember who you were, you're 3, go up and follow parent pointers until you find something bigger than you. Like, that's how that works. Okay, so for example, let's do this and as just like a drawing. Let's say I've got, no, I guess I did enough pictures of that. Let's say that I want to find the successor of 4. Do you see how it's not immediately the first parent? You got to go up a little bit. So like, let's say I want to find the successor of 4. Like, that's my original node n. All right. And what you'll do is you'll remember, like, one way to do it is you can remember, like, what was your original key? That was 4. And you'll just keep on saying n equals n arrow parent. Like, all right, n becomes the 2 node. Compare that 2 to the original key. Oh, no, it's smaller. I'm looking for the first bigger thing I see. So you go up some more. Be like, all right, no, not that one. And then you'll go up to the 5 and be like, oh, hello. I see that you are bigger than 4. You're the first bigger thing, so you must be the successor of 4. Does that make sense? That's what you go looking for. It's essentially you keep going until you notice that you came from the left side of somebody. Your parent you were on the left side of your parent. That's what you finally find the next bigger thing that way. Okay, so that's how that works. There's 2 ways of noticing that. You can either save the original key or just like keep going up until you notice that where you came from was on the left side. Okay, so yeah, that is successor in a nutshell. Either you go right and go left forever if you have a right child, that'll work. Or if you don't have a right child, your successor is above you. Okay, there is one node in the tree where there is no successor, and that's the largest node, right? So this game will not work for that particular node. It will work for every other node, but if you try to start from the 7, you'll go up. Notice that you don't have anything bigger than you. You'll go up again, right? Because the parent of 5 is null, and then you're done, right? You give up at that point. You're trying to find the successor of the maximum node, and that will just never happen, okay? So there's one time that it will fail, okay? So let me show that to you in code. I would like, let's copy in, let's see, which lecture? I assume it's this one. Now I'll copy in the bsts.cpp from the previous lecture, and that gives us some, there's no key value pairs, it's just like data, but I've got a search and I've got an insert, and so I've got a tree that I could make. So let's make a tree. Let's make this tree, just with the keys though. So 5, 2, 7, 1, 4, 3. If I do it in that order of insertion, I'll get this tree. So 5, 2, 7. And then it was 1, 4, 3. So if I do it in that order, I'll get that tree. And then I want to make a successor function. I want to be able to say, hey, cout, give me the successor of, I don't know, the 2 node. So the 2 node is roots left. Successor of roots left. And then that will give me, it's supposed to give me back that node that it finds the successor of, if it's there, or null if it's not. So a pointer, so I can get back, like, give me the data there. Show me the successor's data value. So that's the successor of the 2 node. So I want to be able to do something like that. Okay, so that implies then that the successor operation is going to have this kind of signature. It's going to look like this. So remember that it's tree node stars that are the nodes of trees. So it's called successor. It's going to take a tree node star, call it n or something, and it's going to return back the node that is the successor, the whole node. So tree node star again is the return type. Okay, that's how that's going to work. And so I can ask for the successor of the 2 node. How else do I want to use it? Let's do the successor of the 4 node, because that one we know goes up. So successor of the 4 node. Dun, dun, dun. So what's the 4 node? It's going to be roots lefts right. Again, the successor of that, and show me the data. right? Successor of the 4 node. And then let's do the successor of the 7 node to just make sure that special case doesn't work. So that's roots right. So do roots right, give me the successor of that. Don't try to get the data, because I'm going to give back null, probably. So that's the successor of the 7. Does not exist. Important. So that's a thing. And yeah, let's make it happen. So let me implement those 2 cases, and then also the special case of it not existing. All right. So are there any questions before I go to this code? Do you understand like what it takes, what it returns? So what determines which case of these that we're in is, do we have a concrete right child right now? Do I have something non-null in my right child pointer? I'm at some node. If I'm at this node, I notice that the right of me, right ends right, is null. I cannot do it like that. But if I can, I'll do the first one. Okay? So, okay. If ends right is not null, then I can go right once and then left as long as I can. Sometimes you don't go left at all. Like if you want the successor of 5, just like start at 5, go right once. There is no left to go. You're at the successor already. But sometimes, like for the 2, go right once and then go left as long as you can. That will bring you to the 3, right? That's your successor. So it will work. Oops. There. Yeah, so this is like this is the normal case. Normal / logical case. You want the next bigger thing, the smallest bigger thing, then you want the minimum of your right subtree, if there is one. Go right, and then go left forever. So that's what you want. And so it's n equals n arrow right. We know it's not null. I can do that. Change n to be the thing to the right of it. And then I want to go left as long as I can, as long as there's something to the left of me. So while looking to the left, it's not null, right? While looking to the left, it's not null, go left. Does that make sense, that loop? Yeah. So it will stop. This loop will fail the second left is equal to null. And that means your n that you're at right then and there is the successor. So for example, if we started at the 2, we'd go right once, we'd hit here, and then we go left as long as we can, as long as the left thing is not null. So I'd hit the 3, and then like the loop would stop because 3's left is null now. So we'd stop with n sitting at the 3. Okay? That's how that would work. And so now you're done. So when you're done with this loop, you're ready. When we get here, n's left is null. N's left is null, so we found the successor node. All right? That's how it works. And so return that n that we found. That is our answer for that case. Yay. That is the goal. Are there any questions about that? That's the first case. That's the easy case. Go right and then go left as long as you can, as long as there's something to the left of you. Keep going with the minimum thing in the right subtree. Because now it's time for the else case, right? So if there was nothing to the right of us, like we were the 4, then we must go up. We must follow parent pointers until we find the first thing that's bigger than us. That's one way to think about it. All right? Follow parent pointers until you find the first thing that's bigger than us. Okay? So if the successor exists, and we're in this case, if it's there at all, it's one of our parents. All right? So we have to go up using parent pointers now. So I'll play this game of like original key. So, all right, the original key for us, for this tree, is int keys. Original key is the data at the original end node. Save that. And then I want to go up to the parent. So we know that this node has a parent, or it's the root and the parent's null. So I can go up at least once. N equals n arrow parent. So that's my first parent. And it's just like while that parent is real, so while n is not null, and the thing I see there, right? If it's not null, I can go look at its data now. While it's not null, and the thing I saw, like I went up to here now, n is here. Saying I want to find the successor of 4, for example. N is right there. It's at the 2 node. So like it's not null, but the key that I find there is smaller than the original key. I still need to go up some more. I still need to follow parent pointer. So while Dun, dun, dun. While it's not null and the data at that node now, at this parent that I'm looking at, happens to be smaller than the original key, it's not the good one yet, then I want to keep moving up, right? N equals n arrow parent. So keep going up. So this is useful. There's some short circuiting going on here, which makes it never dereference null if you get to the null parent. Like the parent of the root. So like while there is something there, while n, this parent that I'm looking at right now, is not null, and if that happens to not be null also, this data is too small, I want to keep moving upwards. Okay? Does that make sense? How that's going to keep me going up if n is 4, it starts at 4, and like I see the 2. Like I want to keep going up to the 5 node. Yes? Keep on trucking. And the second this loop stops, one of two things is true, right? One of two of these conditions is what stopped the loop, yeah? We have to figure out which one now. So either n is null, like I moved up so far I went past the root, I never found something smaller. Or sorry, yeah, I never found something bigger. Or, like that could have been what stopped the loop, in which case there is no successor. Or, this is what stopped the loop. I found something where that's not true anymore. I found something, therefore, bigger than or equal to the original key. And because we're not putting duplicates in the tree because of the way we're inserting, it's guaranteed to be the successor. Okay? So that's quite nice. So once we get here, one of those two things are true. One of those things on the either side of that and is what was false. All right, so once we got here, either n is null, that could have been what stopped the loop, or we found a key that's larger. Could have been the other condition that stopped the loop. Okay, so we just have to figure out which case we're in. Honestly, you could just say return n right now. Because in either case, like n could be null, and that's kind of what you want to return if you don't have a successor. Otherwise, it's a thing, but just to spell it out, we could make an if statement if n is null pointer, but this is a useless if statement. So if it's null, that means we didn't find it. We went up so far, like we were trying to find the successor of 7, for example. We went up to the 5, it's like, oh no, that's still smaller, so I'll go up from the 5. You hit null, oh no. You didn't find it, return null. Otherwise, you have a concrete node here that's not null. That means we found a successor. Yay, so that's sad face case, happy face case. We'll return that successor. That's in our n variable. All right, so that is that's kind of the algorithm. And I hope you see, like, we don't really need this if statement because n is either, like if n is null, you can just return n again. See that? Because n is null. So technically, we could just return n always once we get out of that loop. But that, in a nutshell, is the successor operation on binary search trees. Yay. Are there any questions about this code? So normal case, find the smallest thing to the right of you, go right, go left forever, find the minimum thing. The minimum thing that's bigger than you, that's your successor. Otherwise, go up until you find the first thing that's bigger than you, if there is one. So that's how that turns into, you better believe I'm going to ask you to implement predecessor instead of successor in a future lab, but it's going to be pretty much symmetric to this. It's just going to be like, go left and go right forever, right? That's how that will work. Go up until you find something smaller, not bigger. That is how that will work. So once you know one, you can do the other one. It's symmetric. But that is successor, and that is the algorithm. Yeah, let's watch it work. The fruits of our labor. So I made that exact tree. Let's see if it works. So we got 3, 5, and 0. Is that correct? The successor of the 2 node? Yeah, the next bigger thing is the 3 node. It did it. Did that right. Successor of the 4 node, it found the 5. And the successor of the 7 node, I'm not printing the data, I'm just printing the pointer. And the pointer happens to be null, because there is nothing. We're returning nullness if there is not a successor. And so that's the 0 address. So that is correctly saying 0 there. So it does seem to be working. and it's doing the right thing in all the cases, go S. So yeah, that successor takes a tree node, gives back a tree node pointer, takes a tree node pointer, gives back a tree node pointer. Where is that successor, or null if there is not a successor? The next bigger thing. Yeah. Any questions about this example, this code? All right. So let's see. What's the easiest way for me to do that? So I can't really show you all the code at once, probably. Or maybe I can. I could split screen this. Is that at all useful? I don't know. Maybe not. Never mind. I'll just give you the slide because I have a question for you now. Here is essentially the diagram. I think that'll work. But I want you to think about the complexity of that now. So there's successor. It's a little small, but there's the algorithm. You remember what I just did. Let's say that we've got a BST. Its height is h. Like I've made a BST. Its height is h. Like, I don't know what it really looks like. I just know its height. Could have some stuff over there. Boop. Have a bunch of stuff over here. I don't care how long it is. I just know that the height of that tree is h nodes. H nodes tall, or h edges tall. What would be then, using that, and like n is the number of nodes if you need that, what is going to be the running time complexity of our successor operation? And here, let me go back to the written nice page and clear it out. If you're on the page, please refresh it so that it can be a blank slate again. But I'd like you guys to talk about this. Are there any questions about the question? So think about how we implemented it. We had some loops and stuff. I don't know the best way to show this to you. I guess I could show you the code really small. But there's no easy way to do this. If you want to come stare at the screen, that would work. But here's the code. It's got some if statements. It's got some loops in it even. Very small, but you can come up to the whiteboard if you need to look at it. With that in mind, what do we think the running time complexity is? You could use n if you need to. N is the number of nodes in the tree. The height is h. Those are like the two variables you could maybe include in your calculation, but try to think about the complexity, all right? And try to write it down. So please discuss that for a few minutes and let me know if you have any questions and we'll see what you're thinking. Somebody gave you a node. They want to know the successor of it. How many things in the worst case do you have to do? How far away, I guess, could that successor be? That's one question. He's moving around between nodes, right? How much work are you doing per node? Consider the worst case of you moving about that tree. How much work are you doing per node? Because you're looking at nodes, right, until you find a good one. How much work do you have to do at each node you look at? Constant work? Linear work? How many nodes, in the worst case, do you have to look at? Do you have to visit every node in the tree? Yeah, this is tricky. It's interesting. We'll take a few minutes to think about that.
25 for latency. I did get in my attendance.
You shouldn't have done that, but that's good.
I thought it was going to be yours. Wait, I apologize.
Another minute or so to think about it. It's okay if it's a little complicated. You don't get it in time. We'll discuss. Take another minute to gather your thoughts. O if something is the answer. Getting there. All right, another few seconds to write something down, get it in. Yeah. Gather your thoughts. Oh, where do I want to be? Here. Did any questions come up as we were thinking about it that I could answer before I just give away or reconsider yours? How many nodes are we going to have to look at in the worst case? Let's take a look. Let's take a look at our thoughts. We've got, oops. Look at it. We all agree that it's O of H. That seems to be the case for a lot of algorithms. It is going to be O of H. Good job. I guess worst case, if you want to like, I like using H. I told you before that it could have been like search and insert could have been O of N if you had the world's disgustingness looking tree, but still that's H at the same time. I think H is a better thing to be using here. So I like O of H. O of H is going to be the answer. So that's good. Well, let's talk about it. So the question is like, it is going to be O of H. And that's kind of nice because you're either going down the tree or up the tree, right? In either of those two cases, down the tree or up the tree. At each node, you're only doing constant work, right? You're looking at its data, comparing it, and like moving up, changing the pointer around, changing the value around. Either case. And you're never going like up and then down, right? So you're never going to visit like every one of the end nodes or something. You're either going to go up the tree all the way, potentially in the worst case, or down the tree all the way. Does that make sense to us? And so the worst amount of nodes you could go look at and do constant work at then is on the order of the height of the tree many, okay? So yeah, that's going to be the goal. So like, assume you're given a pointer to the node, like somebody gave that to you, right? So the node you want to find the successor of, like that's the way you call it. It takes a tree node star. So in the worst case, you have to visit O of H nodes for, just like the normal case is one option. And the other way, like either case is fine. So like, say you had, I don't know, this tree, like you want the successor and it looks like this. Boop. Disgusting. Oh no, I need a wider arrow. Sorry. So I want to draw this symmetrically. Oh goodness. Let's do that. This is what your tree looks like. Like that's what you'd have to do, and that's the height of your tree. Like this is level H. Like that would get you down to the lowest one, right? So in the worst case, you want the successor of the root, and it looks like this. You have to visit height of the tree many nodes, on the order of height of the tree many nodes, because it's -1 really, right? That many nodes, and that's just how it works, yeah? So the same is true if you did it the other way, if you had to do the parent pointer following stuff, because you could have had a tree that looked like this. Oh goodness. You better believe it could also look like this. Oh, did I do too many? So I gotta keep this even. Boop. Something like that. And say you wanted to find the successor of this node. You keep going up until you find something bigger. Everything was smaller than you. Until you get to this node, yeah? You have to go all the way up, parent pointer land-wise, to the root of the tree. So that's following height many nodes, okay? So that is unfortunate. But either case, you could either have done that or that, and that's you following as many as you possibly could, right? And at each node, you're just doing constant work, right? Constant work, just like looking at the keys value. Either you're there or you're not, right? Looking at the keys value, or like checking to see if there was null or not yet to the left of you for the normal case. And so it's O of H total work, all right? So yeah, it's that means actually that successor didn't need to look like this. It could have been, give me the successor of a node with a key called K or something. Int key, give me a key you want to search for. Because you could go search for that tree node star in the tree, and it would not add to the running time, would it? Because it's also O of H to go search for something. It'd just be O of H plus O of H then. Does that make sense? That's kind of interesting. So we can let it be a two-step process. The user can, like, if they have the node pointer ready for them, they just call it. But it would not change the running time to just start with the key and search for it first. Which is interesting. I mean, it would take technically longer, double the time, kind of, maybe, but double the wall clock time. But in terms of running time, it is still O of H. Isn't that cool? I think that's fun to think about. So yeah, that is, I don't know, that's successor in a nutshell. Are there any questions about it? So I've shown you code. We've got some diagrams. Do you see it and understand its complexity? Let's see, I don't know if it's worth talking about time complexity. It's just like, it's going to be, sorry, not time, but space complexity. Space complexity is constant here. I hope we see that, right? It's going to be like, you got a node pointer, you're moving it around. Sometimes you add one extra variable. So it's going to be constant space complexity. Does not matter the size of the tree. It'll change the amount of time it takes to find something if the tree's bigger, but it won't change the amount of space you need to use. Okay, that's quite nice. Yeah, so that is successor. You better believe that predecessor is exactly the same. It's just the opposite. So like, say you wanted to find, I don't know, the predecessor of the 5 node. Instead of going right and going left forever, you want to find because the successor is the smallest thing that's bigger than you, you want to find the biggest thing that's smaller than you now. So you want to go left once to all the things that are smaller than you and find the maximum now. Yes? So go left and then go right forever. And that will bring you to the 4 node. Does that make sense? So that would be the normal case for the predecessor. The other case for predecessor where you have to follow parent pointers is when there isn't a left child of you. So like, say you got the 3 or something. You want to find the predecessor of 3. It's going to be the 2. So you'll follow parent pointers until you find something smaller. 4 is bigger than 3. 2 is smaller. That's the first smaller thing, so that will end up being the predecessor. So it's, again, you came from a child that was on the right this time, is another way to think about that. Okay? So like those are your 2 cases. You're just going to swap less than for greater than and left with right, more or less. Okay? Any questions about predecessor? Because that's the one I'll ask you to implement. The goal, remember our goal. This is the removal section. We have not really talked about removal yet. We needed one of these 2 operations to do removal. It does not matter which one, actually. So to do a 2 children removal, we can use either the predecessor or the successor. That's why I've taught you this, okay? They're useful algorithms, but this is why I've taught you this, okay? So we will get to that maybe next time because we're running out of time. I want to stop before saying too many things. But there's going to be 3 cases, as you would expect, to removal. The leaf case is very easy. That is just like do exactly what we were talking about. Just like get rid of, like if you want to get rid of that node, just like find its parent, go up to its parent, tell it to forget it. All you do, and then delete it from the heap, of course. For the, that's easy. For the one child case, it's still kind of easy. It's like you want to get rid of the 4, for example. Go away, please. You just kind of like go to its parent, remember which side it was on, just like put its one child on that side of the parent, and whatever was below it is still in the right order. It's fine. And then you can delete that node from the heap. Also change the parent of that thing. That's what you would do. Those are technically the easy cases, even though that one's kind of hard. So like that's easy. 2 children case, disgusting. But predecessor or successor is going to be nice. And either one will work because you're guaranteed to be able to either go left and then right forever, or left and then right. Sorry, left and then right forever, or right and then left forever, because you have 2 children. You can go left once or right once in the 2 children case. So either predecessor or successor will work. And here's a sneak peek of that algorithm. Let's say I want to get rid of the root. There's going to be a trick where we're not going to change the tree as much as you would expect. All right, so it's kind of nice. I'll actually get rid of this because I want to highlight that in a new way. Say I want to get rid of this node right here. What you can do is you can do either the predecessor or the successor now. Find the predecessor or the successor of that node. Let's do, just for fun, the predecessor, because that's different than what we've talked about for most of the day. The predecessor of 5, I know I can find it. It always must exist because I know I have a left child, for example. I can go left and then right forever until I can't no more. I find the 4. So the 4 is my predecessor of the 5, okay? Whee! So there it is. Here's a sneak peek of the 2 children algorithm. 2 children removal algorithm. You will swap the key and value of the node you're trying to delete with this node, and then get rid of it though. So really, it's not really swapping. It's just like bring this up to where you're about to delete. It's like, okay, put the 4 and the A there, but you can also think of it as swapping if you want to. It's just like there's no real need to swap though. Like then you could put the 5 and the high here maybe, but you don't really need to do this last part because you're going to get rid of now. Notice now, if I get rid of this node, it is guaranteed to be one of these 2 cases. I've put a node I put the values that I don't like in a node that's easier to delete. That's the first step. Does that make sense? That's quite nice. I'm guaranteed because I know that because it's a successor or predecessor, it does not have at least one of its children. So it's going to be in one of those 2 easy cases. And then also, I'll just delete this once I'm done. Now we'll bring it in. And then also, this node is okay to be there. This does not mess with the way that the tree is arranged because, like, everything, like, it was the biggest thing that was over here, so it's okay to have that, like, to move it up and get rid of it from down there. And then also, it's also still smaller than everything that was to the right of it, so it's okay for us to put it at that place in the tree, even if it was the root. It doesn't have to be the root, just something with 2 children. Does that make intuitive sense? I think that's really neat. It's a great algorithm. You don't have to mess with the tree as much as you thought you did. We're going to swap with something easier, put the stuff we don't like just for a split second down in a node. Now the tree does look weird. It's not a correct BST, but you're going to get rid of this node right now anyway. Just get rid of it now. It's one of the easier cases. And now you can just call delete on that. So technically it's a recursive algorithm, but you're just going to call delete once more. And then you're going to get to one of these base cases, I guess you can say. All right. So that is, I think, all that I wanted to say about that. That's going to be the trick of it all. But I think that's where I wanted to stop. So try to read ahead if you'd like. Ask me questions if you have any. But I think that's where I wanted to stop for the day as far as content is concerned. Are there any questions about anything we have talked about? I guess I had a slide for midterm 2 info. Might as well talk about it now. Why not? You'll have 2 extra days to study. But I might need to change some of the pages. I didn't look at them yet. So here, you have a test coming up in 2 weeks. Might as well do that because we have a lab to give next time. So maybe this is a good day to do it. So, all right, I will release this midterm 2 module. We can do the info page and the extra credit assignment page. But let me make sure right now that the day is right because it's going to be the Thursday, right? Thursday 2 weeks from now. So it's going to be on the 30th. So Halloween Eve. At least we get it out of the way. It's going to be on the 30th. All right. So let's make sure these pages look right before we get there, before I release them. Yeah, cool. At least I did this ahead of time. Nice. So that's fine. That's fine. Cool. So I'm going to release these pages in a second, but I think I did this right. Oh, no, sorry. This was from the online class from before. I thought I was going to do this on Thursday, so I didn't yet. So the midterm will be during class on the 30th. There. Will be during class on October 30th. It will be an hour and 30 minutes in length. Dun, dun, dun. I think that's all that I wanted to say. Yeah, all the rules are the same, of course. During class on the 30th, it will be an hour and a half, just like the first midterm. So it's 3 Thursdays from now, technically, but 2 weeks and 2 days from now. So that's when it's going to be during class on the 30th. Be an hour and a half, and here are all the topics that I'll be taking from. There will be labs involving trees, but not quite BSTs, I don't think. So lab 7 is the one that I'm going to release next, and let's just for a sneak peek see what it's about. I can't remember if it's BSTs yet. It might just be the tree lab. But we'll talk more about this on Thursday, of course. Yeah, this will be trees, just normal, doesn't have to be BST tree stuff and like recursion, where you do traversals and expression calculation stuff. So do still, though, expect to see maybe something easy about BSTs, because we'll have talked about them in lecture at least, even though you won't have coded up anything. I've given you some code myself, though. But I might just I'll save the harder BST questions for the final. That will be my promise to you, okay? So that's how that will work. And then also, we're going to get to a topic called, let's see. In your readings, at least, there will be a topic called heaps. I think my goal is to not ask you anything about them, but if I ask you anything, I promise it'll be the world's easiest question, because you'll only have read about them, all right? So there's that. Here's a nice list of topics about things that I care about asking you about. I think that's what I wanted to say. Yeah, our next topics are called heaps, and that would be like the week before the midterm, and that would be evil for me to ask you anything that isn't like super easy. So I'll save most of those questions, if not all of them, for the final. So yeah, these are like the main topics I'm going to ask you about. I will also go easy on BSTs. That's my promise to you. Okay? So that's what the midterm will be about. It will have exactly the same style of everything as we did last time. It's closed book as it was last time. You'll just take it on the big computers in this room. You can have a cheat sheet again, both sides, as long as you handwrite it, and you can use as much scratch paper as you want, but that's all you get. Okay? And then here's some sample questions as usual. Are there any questions about the logistics of the midterm? So it's coming up. Don't forget about it. At least we get it out of the way before Halloween. So there's that one. And then with every exam, I like to give extra credit. And so if it comes out on the 30th, I'll make the extra credit be due on the 29th. So the day is a little off right now before I release it. Let me change that right now. 29th. So for everybody, there's no extensions, do not apply to tests or extra credit. So there it is. There's the due date, 29th. Halloween Eve. And the rules are exactly the same as the first one. If you would like to get some extra credit, up to 2.5%, please make a little review video for yourself and for your peers. It's a good excuse to study. Remember that no late submissions are allowed, so get it done ahead of time. If you would like, go over and give a bunch of examples of stuff that will appear on the exam. You've got a list of things. Make up some cool examples. Pretend to give a little mini lecture, demonstrate all the concepts, just like it's a review, right? So give a little review in however way you would like to. And yeah, if you want half the extra credit, 10-minute video, full 2.5%, make a 20-minute video, please. You don't have to edit it or anything. Just go over your stuff and be helpful, and all your peers will love you forever. So yeah, just make sure, as usual, you got to make something new to get that extra credit. You got to make new slides, write some new code. Can't just go over a lab, go over slides that I worked hard on. You got to do something yourself, right? Let me know if you have any questions about your idea. I'd be happy to give you my thoughts. But as long as you do something new and you explain some stuff, go over some examples of stuff that will appear on the midterm, I don't see any problem with that. So yeah, let me know if you have any questions about how to record yourself. The library is also checking out laptops if you think you don't have the technology to do this, like I want to make sure that everybody has the opportunity if you want to. So I can help you fill out the library's form to like check out a laptop so that you can then do this. So yeah, that's the extra credit assignment. Do it if you would like. It'll be due the day before the test at 11:59. Any questions about that? Yes, that's right. Thank you, Caitlin. Yes, do take advantage of that. It is a wonderful, wonderful thing that we have that here in this class. So you guys are blessed. Let's see. I think that's all that I wanted to say about the stuff. I can now release these pages. I think I did it right. So yeah, eventually the midterm itself will appear in this module. If I refresh, the date should be correct, in theory. There we go. So yeah, you can look at these now too, I think, and let me know if you have any questions about them. I think that's what I wanted to say. The page has changed since I started using what? I'm the one who changed it. Weird. I think it's happy. But yeah, I think that's everything that I wanted to say. Any other questions about anything before I let you work? All right. So yeah, I'll give you your next lab on Thursday, and that's just the last piece of this week. So I think that's everything. I will stop the recording now and be here to answer any questions that you have.